Okay, now if you think that the reason why I usually make some weird sounds before actually starting the lesson is because, kalokohan niya lang yan, then I'm sorry, but you're absolutely wrong. That is because, for some reason, when I start recording my videos, it doesn't start recording right away. So I just do some random, not kalokohan, for a few seconds before starting my videos to make sure that nothing is cut. But if you thought, by watching this video, you will be learning about how to linearize absolute value because it is not actually linear, then I am happy to tell you that you are absolutely correct. So let's do it. Okay, so first, we have two cases for now. The first case is when we want to maximize the sum of an absolute value. For example, here we have max z equals the absolute value of x plus y. What do we have to do here? Remember that because of the non-negativity constraint, which is part of the assumptions of linear programming, we know that x is always greater than or equal to 0 and y is always greater than or equal to 0. And x and y will never be negative. And so we can say that the absolute value of x plus y is the same as just x plus y. But why? If you think I planned that in advance, then I didn't, but I am happy that it happened. Remember that this is only not true when x plus y is less than 0. So what do we have to do to linearize this? We just lift the absolute value bars. Max z is equal to x plus y subject to x and y is greater than or equal to 0. And this is the same for case 2, which is to minimize the sum of an absolute value. That would just be min z equals x plus y subject to your original constraints. Okay, clear so far? And if you think that this is too easy for OR1, maybe it is a trick. It shouldn't be this easy. Then I'm happy to tell you again, but you might not be happy to hear that you are absolutely correct. And this is where it gets more complicated. Case 3. What if now we want to minimize the difference of an absolute value? For example, in this case, we want to minimize z, which is the absolute value of x minus y. Sorry. Will x minus y ever be greater than 0? It can, right? Will x minus y ever be less than 0? It also can. So can we just lift the absolute value? No, we can't. So here I will be introducing you to our new friends, S and D. S is defined as the surplus and D is defined as the deficit. And these will be our new objective function variables. So instead of the absolute value of x minus y, we have a placeholder s plus d. And what does this even mean? We will find out soon. We also have this strange constraint over here. X minus y minus s plus d is equal to 0. What? Okay, let's get to that. We can also rewrite this as x minus y minus s minus d equals 0. And you might be able to notice here that what this is saying is that x minus y should always be equal to s minus d. So let's rewrite it like that. X minus y is equal to s minus d. Okay? These two constraints are the same. It's just that in linear programming, we usually have a convention where all the decision variables are on the left-hand side and all the constants are on the right-hand side. But I think it's easier to explain if we have x minus y equals s minus d. Okay. So what does this mean? S is the surplus. And let us define S to take on a non-zero value if and only if x minus y is greater than 0. And let's define D, the deficit, to take on a non-zero value if and only if x minus y is less than 0. How does this work? So, in a normal class, I would ask you to give me two random values of x plus x and y. But in this case, that is pretty much impossible. So I will give you values. Let's say that x is 4. Let's say that, I don't know where to put it. Let's put it here. X is 4 and y is 0. So what is x minus y? That would be 4. And s minus d should be equal to 4, right? Okay. And what do you expect the absolute value to be? That would just be 4 minus 0. And the absolute value of 4 minus 0 is still 4. Okay. So what are possible values of s and d? Can s be 0 and d be 0? No, right? Because this equality will not hold. X minus y is 4. Can s be 4 and d is 0? It can, right? So s plus d, this will be equal to, not 0. This will be equal to 4, which is what the absolute value actually is, right? If we plug in x and y here, we will in fact get 4. But notice, what other combinations are possible? Can this be 5 minus 1? Yes, right? And s and d will be, so a while ago we had 4, 0. Now we have 5. Let me not put it there. A while ago we had 4, 0. Now we have 5 and 1, right? This can also be 100 minus 96. And this is equal to 4, right? 196. And this also holds. So there are an infinite possible number of combinations for S and D. So don't we need a constraint to fix that? The answer is no, we don't. Let's take a look. Z in this case will be equal to 4. Z in this case will be equal to 6. Z in this case will be equal to 196. We know that the correct answer is 4, right? But 6 and 196 are also possible answers that fulfill all of the constraints. But why will it choose 4? Let's go back to our objective function. We want to minimize, right? So in this case, what will our linear program always choose? 4, 6, or 196? It will choose 4. And here we see that s is non-zero, but d is 0. X minus y is positive, so that fulfills what we defined earlier as s, or the surplus, being greater than 0 if and only if x minus y is greater than 0. Alright? Let's try it for another case. Let's try it for, let me just rewrite that. Ooh, let's change colors. This is a good color. Okay, pwede na. So let's have min z, and don't forget the non-negativity. Let's put that later. Equals s plus d subject to x minus y equals s minus d. Ooh, colors. Where x equals, sige, let's leave it at 4, but y equals 10. So if this is an absolute value, what we expect it to be? That would be absolute value of 4 minus 10 equals absolute value of negative 6 equals 6, right? Okay. So 4 minus 10 is negative 6. X minus y will always be negative 6. So what are possible combinations here? Can we have 0 for s and 6 for d? Yes, right? So we put 0 and 6. Can we have negative 6 equals 10 for s and 16 for d? Yes, that still works, right? So 10, 16 is a valid combination. Can we have negative 6 equals 1000 for s and 1016 for D. Sorry, not 1016, 1006 for D. Yes, we can, right? So we can have S is equal to 1000 and D is equal to 1006. All of these are valid. But since we want to get the minimum, what will our linear program choose? Our linear program will choose 0 and 6 because that gives us the smallest sum, which means that we don't have to find a way to make these invalid anymore. We can leave it as is. And what do you notice here? S is 0 and D is 6. What is x minus y? Negative 6. And remember that our definition of S and D a while ago says that S, the surplus, is only non-zero if x minus y is greater than 0, or x minus y is positive. And D, the deficit, is only non-zero if and only if x minus y is negative. In this case, x minus y is negative, and you can see here that only D is non-zero, which fulfills our definition earlier. Alright? And if you think we're done, sorry, but you're wrong. There's one more case. Maximizing the difference. Max z equals absolute value of x minus y. Now, I want you to pause for 3 minutes and think about it. But, after 3 minutes, if you still don't have an answer, please go back to the video, okay? And I hope you went back to the video because I will say that there is a way to do this, but we cannot do it with what we currently know. So thank you. If you spent 1 hour thinking about it, then better luck next time and follow instructions. But it's good to see the effort. But thank you. And good night to you all.